So if you recall from second year introductory physics, you studied electricity and magnetism. Essentially, you studied or developed Maxwell's equations in integral form. So E is the electric field. The idea of integrating the electric field over a surface, right? Electric field dotted into a surface element, a little, an infinitesimal area with information about direction. And this indicates closed surface. And if you recall, this was referred to as Gauss's law. This is equal to the charge inside of this closed surface divided by some number, epsilon naught. Then the idea of the electric field. So this gives you a sense of the geometry of the electric field. And this is true because electric fields diverge radially away or towards charged particles. Because of that, if you, instead of integrating over a surface, but you integrate over a line, and in particular, if you integrate over a closed line or a closed path, then you eventually end up, at some point in the course, recognizing that if you add, and if you have a changing magnetic flux, phi b, where phi b is, by definition, b dot dA, the integral of the magnetic field over a surface, then this is equal to 0. Right? So this also captures cases where the electric field may circle around, whereas if you don't have a changing magnetic flux, this term disappears, and you have that electric fields don't circle around, they only diverge radially away. That's sort of the content of these equations. And the same thing for magnetic fields. You explored the integral over a closed surface of the magnetic field, so B dot dA. And because magnetic fields circle around the source of the magnetic field, this is always equal to 0. In some sense, you're not capturing the field with surfaces. If a field line comes into a closed surface, it must come out somewhere else. Overall, that leads to a 0 magnetic flux through the closed surface. But magnetic fields do circle around current, and therefore, when you do this calculation, right, whereas electric fields are only in a special case, is this thing not equal to 0, namely it's equal to minus d phi b by dt, this is equal to, in other words, in terms of sources on this side, here we always have something, right? So we have the possibility of a source term here, whereas here you don't. Here you also have a minus mu naught epsilon naught d phi, just like this, e dt, where now phi e is the integral of the electric field over a surface. So changing electric flux appears here, and electric and magnetic fields start to look a little bit more like each other. Right? So you also explored the idea that maybe there's a possibility for a non-zero term here that would make these equations more symmetric. In this course, you're going to explore the same Maxwell equations, but from a different perspective, not in terms of integrals, but in terms of derivatives. So integrating the electric field over a closed surface is sort of a way of capturing electric field lines, and you can capture them by surfaces. Another way of asking the same question, right? The reason why you can capture electric fields with surfaces is because electric fields diverge radially away or towards charged particles. So another way to ask that question is, how does the electric field vary radially? And that kind of operation is called the divergence. And so this is a kind of derivative of the electric field, right? So there's a dot product here. So this is some kind of operation. It's a vector operation that gets dotted into the electric field. It's a kind of derivative. And the answer to this is the charge density divided by epsilon naught. This object has the same information as this object. In fact, we will be able to take this object and turn it into this object, and vice versa. So for this equation, there's a differential version of this equation, which says the reason why the electric field has a non-zero integral around the closed path is because there's an electric field that curls around. And so we can ask, is there a differential operator that captures the degree to which the field curls around? And that's this object. So this is a different kind of derivative. This is asking how the field curls around, and it gives you a vector. And so you end up with a vector as a result of this. And here we have a term that involves not an area, but a field, so dB by dt, and that is equal to 0. And then we do the same thing for magnetic fields. We ask, does the magnetic field diverge? Does the magnetic field curl? And so the divergence of the magnetic field, right? Because magnetic fields don't diverge, they only curl around, this thing is 0, and so the divergence of the magnetic field is 0. Magnetic fields don't diverge, have no divergence. And so these two equations have the same content. And then we can ask about the curl of the magnetic field, just like we did here. And so here we get a minus mu naught epsilon naught. We get rid of the surface here, and we get dE by dt. And that ends up being mu naught times a density of current, whereas here we get current itself, right? Because we integrate this to get current over a surface and to turn this thing into an integral equation. But this has the same content. So this course is really focused on understanding the divergences and curls of electric and magnetic fields.